Saxon Advanced Mathematics, lesson 25. It's a two-parter. The first part is short and sweet. The second part is going to make your hair stand on end. It gets a little crazy. I'm not saying it's hard, but I'm going to say it gets a little crazy. More on that later. The first part, one example, we're talking about age problems. We did these at the end of Algebra 2. The trick is just in setting up the variables. The actual solving isn't hard. Let me read you the problem just to give you a feel again for how these work. 10 years ago, Thomas was twice as old as Patricia. 5 years from now, Thomas will be 10 years older than Patricia. How old are both people now? Okay, so the trick is to set up a chart in which we will say, here's the age of Thomas now, here's Patricia now. And I'm going to write this in the middle too, because this will help us. Patricia, that's a P. Okay, 10 years ago, they would be the age they are now minus 10. The other timeline in the problem is 5 years from now. So that's in the future, so that's their age now plus 5. Okay? Technically, we don't need this column, but it does very often help students just kind of see the flow of this. I like to put these in chronological order, right, from longest to go to the future, just to help this all flow together in your mind. All right, now we've got variables for these two different time frames that are as similar as possible, right? We're not just using completely different variables, we're linking them. Now we're ready to set up our equation. The first statement is about their ages 10 years ago. 10 years ago, Thomas was twice as old as Patricia. So, Thomas 10 years ago was older than Patricia 10 years ago. How much older? He was twice as old. So he's already, his number is greater, so we have to multiply her by 2 to get this to equal. Make sense? And now the second one is that 5 years from now, he will be 10 years older than Patricia. So in 10 years, Tn plus 5, in 5 years, I think I said 10 years, he will be 10 years older than her, so he's still going to be older than her in 5 years. But this time, instead of being twice as old, he's going to be 10 years older than her. So I'm going to increase this side by adding 10 there. There's my system of equations. All right, let me clean them both up and see what I've got. This will be A, this will be B. I'm going to distribute here. Okay. And then I'm going to do what we normally do when we have systems of equations. We kind of like to go first variable, second variable, plain number on the other side. So I'm going to swim the Pn over this way, and I'm going to add the 10 to both sides. So then I'll have, that will cancel, I'll have Tn minus 2Pn equals minus 10. Okay, that looks pretty cleaned up. And then this one, this is my new A. And then my new B, let's see, it was Tn plus 5 equals Pn plus 15. So I'm going to subtract the PN from both sides, and I'm going to subtract the 5 from both sides. All right, again, I'm bringing both letters to the left and pushing the number to the right. So then I'll have TN minus PN, that cancels, equals 10. Okay. So now I've got this and this, and I'd like to eliminate here. That's been my goal all along. I could substitute, but I prefer to eliminate. So what I'm going to do, I'm going to multiply this top one by -1 and get my TNs to eliminate. So this will be -1 times A, and I'm going to write it down here, minus TN plus 2PN, right? This minus turns out plus, equals positive 10. And because I don't want to turn the page, I'm going to draw myself a box, and I'm adding these together, and I'm going to go up here. These cancel, and I will get PN equals 20. Oh, that worked out really easily, didn't it? So Patricia now is 20 years old. And so how do we figure out how old Thomas is now? Well, look, this one's perfect. TN minus PN equals 10. So he must be 30. Now, and let's see, those are the correct answers, P.S. Let's just see the original things. 10 years ago, he was twice as old as Patricia. Okay, so 10 years ago, he was 20 and she was 10. Yeah, that's twice as old. 5 years from now, he will be 10 years older than her. Well, that's true because he'll be 35 and she'll be 25. They're 10 years apart. So, in any case, this is the right answer. Yay. The trick is in the chart, right? This is fairly straightforward. You know how to do that really well. The trick is just setting up the variables to do the ages, all right? All right, now enough with about age problems. Now we're going to do some rate problems. And up until now, dun, 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 fateful words. Up until now, we've always called these dirt problems, right? Because we've said distance equals rate times time. What we're going to do is we're going to take this and we're going to change it ever so slightly. We're going to keep the rate times the time, but instead of looking at this product as the distance, we're going to look at it as a job, okay? You could say in these, the job that everyone was doing was traveling, so the distance was the job that they were doing. But we're kind of globalizing this concept by saying it's not always a distance. Sometimes the rate times the time can equal a job. Now let me read you a story, and then we'll break it down and figure out what to do. By the way, in most of these problems, the key is to figure out the rate and then use that to calculate. They're kind of two-step problems. Joe Frank can wash 3 cars in 5 hours. Okay, so I'm going to write that down right away. First, let's do this though. 25.2. The rate of Joe Frank equals, what did he say? 3 cars in 5 hours. And just to make life even crazier, we're going to keep track of the units in these. John wants us to get more practice in canceling the words and making sure that it's all sorting out. So we're going to practice doing that, and it'll be fine. It's just one more thing, right? And Meryl can wash 4 cars in 3 hours. Whoa, so fast. I question the quality of the workmanship, but that's not a part of the problem. 15 cars need to be washed. So 15 cars equals the job. All right, if Joe Frank works for 2 hours and is then joined by Merrill, how long will Merrill and Joe Frank have to work together to finish washing the 15 cars? Do you have a headache? I do. That's annoying. Okay, so here's what we want to figure out first. Joe Frank is working alone. How many cars does he wash? How many cars can this dude wash alone? His rate is 3 cars per hour. Again, we're keeping the words in there. He works how long? He works for 2 hours by himself. Times 2 hours will equal a certain number of cars, right? Okay, how do we solve for this? Oh, well, we just smush these numbers together, right? That equals, this cancels, and we will get 2 times 3 is 6 over 5, right? I'm just simplifying that. That is how many cars JF can wash alone, all right? So that means when the two start washing together, they don't have to do 15 cars anymore because this dude has already done that, okay? So our new job is 15 minus 6 over 5 cars, right? Because Joe Frank already started. So we better multiply this times 5 so that we can subtract. That is 75 over 5, right? And now we subtract. That means the new job is 69 over 5 cars long. All right, so I'm going to take that to the next page. Okay, so I'm going to make a little shade for myself. Beautiful. So the job equals 69 over 5 cars. Now we know that the rate of Joe Frank times the time that they're going to work together. So they're working together, so I don't need to make 2 separate times. I know it's got to be 1 time. The rate of Joe Frank plus the time plus the rate of Merrill times the time has to equal 69 over 5 cars. Because that's the amount of job that's left. Oh, it's kind of confusing, isn't it? All right, the rate of Joe Frank, this I wrote on the other page. He is 3 cars per 5 hours times T, that's what we're solving for, plus Merrill was 4 over 3. 4 cars for 3 hours times the time, whatever that is, will equal 69 over 5 cars. Let's blow up some denominators, shall we? Our least common multiple is 5, 3, 5, it's 15. So we'll multiply every one of these fractions times 15, every term. This will be 3 times 5. I should have canceled here, not the word. And 3. So now, simplifying this, I have 9 cars per hour times some time plus 20 cars per hour times that same time equals What's 69 times 3? 27, 18, 19, 20, 207 cars. Whew, that's a lot, isn't it? Okay, but we can now add these together, can't we? So it's 29 cars per hour times the time equals 207 cars. And now we can divide, because we're trying to get this t by itself, right? So we'll divide by 29 cars per hour divided by 29 cars per hour. Look what happens. This all cancels by design. I was trying to get that t by itself. This number becomes, the time is equal to 207 over 29. Now let's look at the units. Units behave just like numbers do. So if we've got a complex fraction, we multiply this one by hours over cars, hours over cars. The cars cancel, this all cancels, and we're left with hours, which is exactly what we want. That is our final answer. It is wildly unsatisfying. If you simplify it with a calculator, what's the answer? No, John doesn't give it to us. I thought I figured it out, but I'm not seeing it. That's the answer, though. Okay. In this one, the dude worked by himself first, so we had to figure out how many cars he got done, and then we used this to set up the second part of the problem where we figured out them working together. These problems are not easy because there's so much going on, and we're going to get more complicated in just a minute. But you just have to go methodically and logically and work them through. Let's try another. The other thing you'll find is that John makes very strong patterns. So if you have a homework problem that you're struggling with, come back and find the example that works just like your problem. He tends to make the patterns very strong, and then you can use that as a bit of a step-by-step. Okay, 25.3. Maya could empty 2 bottles in 3 hours. Okay, so the rate of Maya equals 2 bottles every 3 hours. Working with Wilbur, she found they could empty 4 bottles in 3 hours. Okay, so the rate of Maya plus Wilbur equals 4 bottles every 3 hours. What was Wilbur's rate of emptying the bottles? Okay. We know that rate times time equals job. Let's just get that in front of us. And in this case, our job is bottles. Emptying them technically, but we're just describing it as bottles. Okay, so that means that the rate of, what's her name, Marie? No. Mayha. M-A-Y-H-A, Mayha. The rate of Maya times the time that they're working together, plus the rate of Wilbur times the time that they're working together, is going to be 4 bottles. I'm sorry, 4. It's going to be the bottles. And we know they're working 3 hours, so we can plug that in. Okay, I can put hours on this. All right, that's the time they worked together. That's how much they accomplished. Now we'll put in the rate of Maya because we know hers. So 2 bottles for every 3 hours times 3 hours, because that's how long they work together, plus the rate of Wilbur times 3 hours equals 4 bottles. Oh, that's so tricky to understand. We're just plugging in what we know and using this pattern as best we can. All right, this cancels, right? And what we can do is we can subtract 2 bottles, right? I'll write it out this time. I just wrote a B there. And what we get is the rate of Wilbur times 3 hours equals 2 bottles. And then we can just divide away the 3 hours. And we find that the rate of Wilbur equals 2 bottles every 3 hours. And that's the correct answer. If you notice, way back here at the beginning, we were told she did two bottles every 3 hours, and together they did 4 bottles every 3 hours. We could kind of intuit at that point that, well, if she does 2 and they do 4 altogether in the same amount of time, he must be working at the same rate she is, because her 2 bottles and his 2 bottles would make 4. But we proved it the hard way. All right, so there is another type of problem. Now, are you ready? I'm gonna make it even a little trickier. I think these problems are some of the roughest things that we do all year. They're just so tricky to pin down. Example 25.4. Okay, just a hot minute ago, I said that rate times time equals job. And that's true, but we can expand this even further by saying rate times time times a number of workers equals a job, right? This implies that just one person is working, but sometimes our rate will take into account how many different workers there are. So in these problems, just like we did there, sometimes in the last ones, sometimes the first thing that we want to do is we want to solve for R. Very often that's our first step. And look, we can just take the formula and divide it by T times W and find that that's a pretty good formula. Is the rate is always equal to the job divided by the time times the workers. Okay, this is a very useful formula for doing these problems. We can back into it. We don't really have to memorize it, but it's helpful if you just keep that straight in your mind. All right, if 5 workers can do 1 job in 8 days, if 5 workers can do 1 job in 8 days, I just found my rate, right? If 5 workers can do 1 job in 8 days, how many workers would it take to do 3 jobs in 7 days? Okay, hold on. We're gonna get to that, but I'm gonna fix up my rate just a little bit more. My rate equals 1/40 worker days. That's the way we want to write this. I multiply those 2 together and I call them worker days. All right. So John wants to know now how we can use R to answer his question. Okay, so that is a pretty common sequence of events for these problems. Solve it for the rate and then use that rate to answer the question. So now he wants to know what would it take to do 3 jobs in 7 days. So all we have to do is take, we know it's our rate times our time times our workers. So our rate is 1 over 40, and I'm gonna do W dash D, worker days, times the time, which he's giving us 7 days. I'm gonna put everything in parentheses, times 7 days, times the number of workers we don't know. So that's my variable. And it's 3 jobs. Okay. It's kind of a lot, isn't it? It's confusing, but that's our rate. We just figured that out. John tells us we have 7 days. He wants to know how many workers it would take to complete 3 jobs. So we're filling in what we know, and we're going to solve for what we don't know. To get this W by itself, we're going to multiply by a reciprocal. 7 days needs to be on the bottom so I can cancel it. And 40 worker days needs to be on the top so I can cancel that. So then I'm going to multiply over here 40 worker days over 7 days. And we'll see what happens there when we do all of that, okay? So let's see. This cancels that, and now I've got this by itself. W, the number of workers, equals, now days cancels days, and I've got 3 times 40 over 7 workers. So my words worked out. This jobs we don't really need to have there. And there's our final answer. 120 over 7 workers is how many it would take to do that job. John goes ahead and reduces this to a decimal number, which is W equals 17.14 workers. That doesn't really impress me. I just as soon have it like that, but that's the right answer also. Okay, so what did we do? We solved for the rate by using this formula, which is just based off this, and we created the rate, and then we did rate times time times workers. We knew the rate, we knew the time, we didn't know the workers, but we knew how many jobs we were trying to finish. Woo! That's a crazy one. And this next one is our last problem for this lesson. It's my favorite problem, but it illustrates the same kind of complicated situation. This time we have workers who are babies. Oh, that just kills me. That just kills me. These babies are assigned to the task of drinking 252 gallons of milk. Okay? There are 42 of our infant workers, and they're on the job for 12 days. So, rate times time times workers equals the job, and we're trying to identify the rate, so the rate equals the job divided by the time times the workers. Okay, their job is drinking 252 gallons of milk. All right, so the rate equals the job 252 over 42 times 12 infant days. And this is gallons. Okay, so that is the rate at which our industrious little cherubs are sucking down milk. We're not going to reduce those numbers. We're just going to leave it like that for now, okay? Now, what happens? So that's our step one. Solve for R. All right, now in step two, some things are going to change. We're going to use R to answer the question. And here's what's happening. Then 14 more infants were placed in the nursery. So the number of infants now is 42 plus 14, which is what, 56. So we've got more workers and we've got more gallons. So our job just increased, 48 more gallons. So we have 252 plus 48. Now our job is 300 gallons. So now we're going back to our original equation and we're going to use that. We've got a rate and we're going to use that to find, the question is, how long will the milk last? We'll be solving for T. Now this has to reduce though. This is 42 times 12 over 252. Let's multiply 42 times 12 and see what we get. It should be, our rate should be 1 gallon for every 2 infant days. This should reduce, but why does that not look like it should? Oh. I see, that's wrong. Yes. So this number becomes 504. 42 times 12 is 504. And I can readily see that 252 is doubled to get that. So this rate reduces 1 gallon per 2 infant days. So in 2 infant days, a baby can suck down a whole gallon of milk. Okay, so that's the rate we're going to use, and we're going to plug our new data into this equation and grind it through to solve for time. Okay, so our rate, I'm just going to write this down, rate times time times workers equals job. Our rate is 1 gallon for every 2 infant days. The time that they have to drink this, we don't know. So we'll just leave that plain T. The number, whoops, that shouldn't be a W. The number of workers that we have has gone up to 56. Infants. And the job that they have to complete is 300 gallons. Holy Moses, right? Okay, so now we want to get t by itself, right? That's our job. So we see that what we're going to want to do, we can cancel this infant against this infant, and we'll multiply by the reciprocal, which will want 56 on the bottom, right? Because we want to cancel it against that. And we'll want 2 on the top. 2 days. And then we want gallons on the bottom. Right? And so then we'll multiply over here. It'll be 2 days over 56 gallons, right? I'm taking gallons from up here and canceling it down below. There's 56, and I want to cancel it there. That's how many infants there are now. Days cancels against this, and 2 cancels right there. Hard to see. All right, so there's my reciprocal. 2 days over 56 gallons, and that's what I've done over here. All right. Now, I've got t by itself. Two days times 300 gallons. The gallons will cancel, and it will be 2 times 300, which is 600, over 56, and days is our final unit. That reduces because 8 goes into both of these numbers. And so our final answer is t equals 75 over 7 days. That is an extremely difficult problem. Trying to let your brain sort through all of this chaos and process changes and translate babies into workers and gallons of milk into their job. That is a lot to tax your brain. If you could follow that even at all, you're doing great. And by the way, this ends up being just over 10 days. It's almost 11 days. So those babies are gonna be very busy on the job, working away. I can just see this like old like steampunk style factory with all these babies lying in their old-fashioned cots and like bottles hooked up on the sides and them just like sucking madly away. It conjures up quite a picture in my mind. All right, that is the end of lesson 25. Like I said, that's pretty freaking hard. When you find the problems in the homework, feel free to look back at the examples and use your notes if need be, which I would need them. Use your notes to follow along and step out the logic. For the first 2 or 3 lessons that you're gonna do these problems, they will probably scramble your brain. That's okay. I'm hoping that after 3 or 4 times through, you'll start to think, oh, this is actually making a little bit of sense. So if right now, if you feel a little panicked, don't worry, I would too. Okay, that's all. Thank you, goodbye.